Hello, I am finally finished with my project here. So in my last video, I finally got the full adders working and understand how they work and function and can build them pretty confidently now. And I realized that I could conjoin a encoder or two encoders to four adders to make a 4-bit calculator. And basically that's what I've done. So this is a 4-bit adding calculator. I can add two numbers together up to 15 digits, so 0 through 15, which means I can have an output of up to 30. So I can add any numbers together that equal 30, basically. One number being up to 15 and the second number being up to 15. I'll kind of give you the tour here and show you how it works. So this is the brains of the operation. Anytime I do flip a switch, this pulses go through this, and this is what computes and gives me my output. This is kind of a monstrosity here. I learned quite a few tips and tricks doing this, which is good. I'm glad I forced myself to complete this because this was a big project. 90% of it was running every single one of these lines like piece by piece, and then having to do the power, repeaters and stuff, and it's just kind of a lot. But yeah, so there's the adders. There's the first half adder because it doesn't need a carryover, and then my three full adders. In fact, let me show you this way. We'll do this. We'll do this a better way. So here's my input bar. You can think of this as like your keyboard or whatever, just your input. So the top row is an A, bottom row is a B signal. If I look underneath here, the bottom row is all going on the ground, feeding this first set of encoders, which is right here. So these encoders right here are taking those 15 input signals and converting it to binary. The second row of input of those levers is coming out right here, you can see, right here. And they're feeding this second row of encoders. So they just skip over these first four, and then they activate these four. So I have both of my input lanes feeding two 4-bit encoders, and then I just have them carrying together. So I have a total of eight lanes here, but each one is separate. So I have a 4-bit and a 4-bit, and then I have this lane and this lane split off, and that's the input to my first adder. So I have lane A of signal A and lane A of signal B, right, feeding my A input, and my B input, etc., etc., etc. So they all come here. Each one goes into the adder where it's supposed to go. It does the calculation, and then a couple things happen here. I realized that I had these flipped, so this is outputting my 1, 2, 4, 8, and then right there's my carryover for 16. So from this point of view, when I built it, I was like, sweet, I'm gonna be all set. But then on this point of view, when I'm actually operating it, it's backwards because my 1 is over here, 2, 4, 8, and that's backwards. Binary goes from right to left, not left to right. So what I had to do is I had to build this monstrosity of steps here and then invert it. So I have this one coming down first and then coming in. So then I just flipped them. So if I flip a switch here, there's one. You can see both of these are one. This is one for signal A and one for signal B, or just separate them. I can do 2, and I can do 2 up top here as well. It will also go through there. I can do 4 for the next bit. I can do 8 for that bit, and then I can't do because this is a 4-bit. I can only go up to 15. So if I want to get that 16th bit, I have to do 15, which is all of them, plus 1. Oop. Oh, and if they're so the reason why it didn't work here is because I have signal A, this top row, flipped over there, and also this top row over here. So in order for this to work, this is a calculator again, I have to add two separate numbers. So this is one number, this top row is one input, this bottom row is the other input. So I have to flip this bottom one. Oops, that is not, that's not flipping it. There we go. So now I'm adding 1 to it, and then that'll give me my 16. Let me get this back to dark here, just it's easier on my eyes. So there, now I have 16. So 1, 2, 4, 8, 16. So obviously I can use any inputs that I want here. So I can do, we'll do 10 plus 7, which will give me 17. So 16 plus 1 is 17. Let's see where my switch is at. There we go. Oh yeah, it's pretty cool. It's a adding calculator that can add up to 30. It's pretty much all it does. This is quite a bit of work to get this working though. I mean, just you can see how much lines it was, and it was literally just like going like this, you know, for a couple hours, and then doing it again for the you know the electricity lines, and yeah, it was a lot of work. There's probably some shortcuts or mods or something to like do this stuff faster. But what I've learned though is to do stuff efficiently. So keeping my signal encoded for as long as possible is a key just for efficiency, because as soon as I decode it or I'm trying to carry an uncoded message, it's a huge message, because again I have 30 inputs here on this panel, but I'm paring it down to eight lanes of data. So it's way more efficient to do that. And one thing to think about, well, you know, let me show you this really quickly. So I have these splitting off to give me my output there, but I actually have something else going on here. The primary lanes on the output of all these also are going this way, and going over here, and then going on these lanes over here to this position. Now, what I'm doing here, I've only done 2 because I don't really see a reason, there's no reason to do the rest. I am decoding signals here. So I am telling it that this lane will operate when there's, this lane will operate when the total equals 15, and this lane will operate when the total equals 30. And I'll show you what I mean by that. So when I hit this, these outputs are just a binary number, right? That's all it is. It just gives me, you know, I'm encoding the signal to binary, and then my output is binary still. But a decoder can decode that message. So even though I have all lanes running to that spot, I've set conditions here. Again, so when this is 15, I get a frowny face. If I set this is 15, I still get a frowny face because the output is 15. And that decoder says that when it's 15, give me this output. So, you know, it doesn't have to be a number. It can be anything I want. I can say, hey, when I have face plus face, or when I have frowny face plus frowny face, give me a happy face, right? So you can do all kinds of stuff with this. And what I've done here is I'm just showing that, so I only have 2 things decoded right now, 2 signals decoded. I can have, again, because it's a 4-bit calculator, I can have a total of 30 outputs here. So I can have 30 separate outputs, right? And then let me show you one other thing, which is kind of crazy to think about. So my limitation for how much data I can carry on this is right here, is these encoders. With 4 bits, you can count from 0 to 15. That's why I have 15 plus 15. So 15 on this lane, 15 on that lane. That's why I'm limited to 30 digits on my output. If I have just one more lane here, let's say I had 5 lanes here, you know, so I could encode a signal onto 5 bits, 5-bit encoder. What that would do is double the amount of inputs I could have, and it would also double the amount of outputs I could have. So you can imagine with just that one extra bit, that one extra lane, this whole thing would be double. So it would be like out to here or something. Probably be like 60, I'm guessing like 61 or 62 or whatever. So I mean, you can have so much data encoded in 5 lines, and that's really shown, reinforced the notion of how efficient binary is compared to like a raw signal. Yeah, it's pretty gnarly stuff. I actually do this kind of stuff at work. Well, I don't do this stuff, but I deal with this type of technology. I'm in the internet industry, and we have analog signals, QAMs, what we call them, quadrature amplitude modulation, where we manipulate radio waves up and down, left and right, the amplitude and frequency, and we pull those frequencies and convert them into binary, and transport it, through just on-offs, which are ones and zeros on fiber, just light, just on off, millions of times a second. And then on the other end, a modem just decodes that signal. So it's the same process. It's but it's much more advanced, obviously. But it's cool to see in action. So yeah, I think that's pretty much all I wanted to cover. In the future, I'm really gonna try and build, take advantage of building vertically, not just horizontally, and using space more efficiently. Because again, like having to build all these lines way out here, and then taking them all the way back, and then encoding them, like I should have just built the adders, right here, and then done the next step right here, and then done the whatever, and just trying to be more efficient with it. I think it's going to save a lot of time, a lot of space, and and doing stuff like this where I'm going, vertical, and then doing calculation, then either going up or down, and or splitting it and doing stacking on top of each other, because there's no reason why I couldn't have this second set of encoders just be on top of these ones, and then all my outputs would just be right here. So it'd be a lot more space saving. So yeah, this is a 15-bit. 15-bit, a 4-bit calculator that can only add. So subtraction is my next task. I don't think I'll build a giant thing like this, because I understand the concepts at this point. I just need to understand how to build them, so eventually I can manipulate the data. I guess in closing here, I'll show you how these things I'll just show you these in action. It's pretty fun to watch. So if I do like a 9, if I have a 9, I'll add 12 to it. You can see all the lights going on and flickering and doing the calculations. I'll add 13. I'll add 15. It's pretty cool. It's just on off, yes, no, if, and or whatever, and then gives me my outputs. So, pretty cool stuff.